So in this lecture we are going to introduce the complex integration, and later on we will try to see an important theorem in complex analysis which is known as the Cauchy's theorem, and sometimes it's also called as the Cauchy-Grissart theorem. So the first remark that I want to make regarding complex integration is that complex integration means that, let's say you have a function of complex variable f of z and you want to integrate it. So from this point of view, this is analogous to the real variable integration that you see in your calculus course. So what we are going to do is that at first we are going to see integration along curves in complex plane. So this is what we're going to discuss in this lecture mostly, and later on when we do residue calculus we'll see a broader horizon that complex integration offers us. So this is the main topic for today, that is integration along curves in a complex plane. And we will see that we can derive some new results for analytic functions, and that result is that this Cauchy's theorem. So let us begin. Let's say we can have a function like this, f of z, and this function can be parameterized in terms of a parameter t. T is a parameter. Now, if you want to write this integral f of z dz, you can write it as, let's say you define the parameter to take values in between a and b, and you define it like this: a equal less than t equal less than b, like this. Okay, so this is a parameter, and note that this parameter will not be visible on the complex plane, because in the complex plane you only have the x coordinates and the y coordinates, or so to say the real part and the imaginary part. This is something that runs in the background and so on. So using this parameter you can write this integral as a to b f of z of t, and you will have this z prime of t dt. This z prime of t is nothing but the derivative, this guy over here, and this is pretty easy to do. You just use the chain rule. You just take this dz, that means dz of t, that means we have z of t, and then we want to take the differential, then this will be just dz dt dt. That's it. Simple. So this is one way to do it. Now another way to do this kind of integration is that, let's say you have some kind of a function that is a complex function f of z, or let's call it g of z, just so we don't get confused. Let's say g of z, and you can write it down in terms of u of xy, the real part and the imaginary part, right, in terms of xy. Now all these x and y's, let's say you can parameterize them with some parameter capital T. So as a result you can parameterize u and v in terms of capital T, which is another parameter. So in such case you can do this integration just by doing the integrals over here. That means this g of z dz would transform into g of capital T dt, and you would have u of t dt plus I v capital T dt. And we'll see some examples at the end of this lecture. So both of these things, that is the one form over here and here, they represent the same result. It's just a choice of parameterization that you have. So you select the kinds of parameters that is most convenient for calculation, and then you proceed with it. Now before we move on, there is a thing that we need to discuss, that is that if you have a curve on a complex plane that is parameterized at every point with some parameter t, and let's say this is our curve, let's say you are going from A to B, then you would go this way, right? So, and if I tell you that you are going from B to A, you would have to go this way. So the very direction of how you traverse the curve is an important thing over here. So these complex integrals are similar to line integrals in vector calculus, and they correspond to the surface integrals via the divergence theorem. So this is how this line integral captures the 2D information that is going on around in the complex plane. So this is one way to see it. Now the thing we wanted to discuss is that this direction thing, right? So let's say we have a parameter. This is our parameter t, and this t belongs to some closed interval a to b. Then for every such t, that is between a and b, we will have a pair of points denoted like this: x of t, y of t. That means x and y, they're also parameterized in terms of t. And for every t between a and b, you will have a pair of points like this, okay? And these are called image points. And these image points will eventually lead us into this evaluating these integrals and the results. So since this is a line integral or similar to a line integral, the direction is important, as I said before. So what we do is that we order these image points, that means these x and y's, we order these image points z of t, because z comes in terms of x and y, and x and y is actually parameterized in terms of t, so that's why I'm writing it as z of t. These image points according to increasing t. This is a general rule of thumb unless otherwise specified. So what does this mean? So if you think in terms of very simple terms, let's say this is a curve. Even though it's a closed curve, what we'll discuss in a bit. Let's say you are going from point, okay, let's not take it to be a closed curve, let's just deal with open curves for now. So let's say this is A and this is B. So along this curve, let's say we go like this. So in this direction, let's say the values of z of t, or z which is coming in terms of x and y, and eventually x and y is coming in terms of t, whatever that is. So this value of z is on an increasing manner, so that would be our positive direction. In other words, it's a very general rule of thumb to take the counterclockwise direction as the positive direction and the clockwise direction to be the negative direction, and this will be important when we discuss with the closed curves that arrive in the complex planes. So this is one way to see it. And this z of t is continuous and differentiable if x of t and y of t are continuous and differentiable. That means your z, that means the differentiability and the continuity of z actually depends on x and y as well, because z is coming in terms of x and y, right? So with that, let's introduce some kinds of curves that we will see in the rest of this course. And the first thing we're going to discuss is that a simple curve. What is a simple curve? The definition is that it does not intersect itself. That means if you have a curve like this from one point to another in the complex plane, this can be regarded as a simple curve. So the formal definition would be, for a simple curve and for two different value of the parameters, let's say at point B or some other point, the value of the parameter is t2 and this is not equals to z of t1 if t2 is not equals to t1. However, this is a simple curve and it's open. Even though it does not intersect itself, we can have simple curves that closed on itself. That means we can have something like this. A circle, say. See, it does not intersect itself. The starting point and the ending points are the same, so that's why I'm using the word enclosing. So this is also a simple curve, but it encloses on itself, because if you take all the points over here, let's say here, here, you can see that for different parameters, a convenient parameter would be the angle itself, like this, the theta. You can see that all the points are different and all the parameters, that means the value of the parameters on these points on the perimeter of the circle, are also different. Apart from this point, let's say this is our starting or ending point, here the curve encloses on itself, and this is also a simple curve. So this is a simply closed curve, and this is a simply, I wouldn't say open, but you can call it an open curve as well, open slash not closed curve. So these are simple curves, and then we will have the non-simple curves. So in the non-simple curve, let's say you have this figure of 8 type of thing. Here you can see that at this point over here, if you start from, let's say here, this is your starting point, and you go like this. Let's say at this point there is some parameter value, that means z of t1, this is some value. You go over here and then you enclose this thing, and not only that, it intersects it with itself. So what I'm trying to say over here is that, notice the first line, the green lines. When you go like this, you hit some value of the parameter, let's say t1, and once you pass this point and you go like this, notice the red line over here, there could be another parameter value, let's say t2 and now you can see that this intersects with itself, right? So that's why we're saying that this is a non-simple curve. And since this is also a closed curve, it's called a non-simple and closed curve. And you can have other kind of curves, let's say like this. Here you can see that the curve intersects on itself, but this is not simple and not closed, right? You might think that okay, this might be a closed part, but that is not the case. By closed we mean that the starting and the ending point, they are glued together. Okay, this is just an intersection, that's it. So how do we traverse these curves? Well, again, as I mentioned before, when we do this when we do traverse these closed curves, we in general take the counterclockwise direction to be positive unless otherwise specified. Okay, so let's say you are having this simple closed curve and you are trying to integrate something along this curve, right? You would denote it with a closed sign. This is not that important, this circle on the integration sign, but it actually means that it's a closed circuit integral or a closed contour integral. And if you take the counterclockwise direction to be positive, then the anti-clockwise direction, the clockwise direction would be negative. So if this is the clockwise direction, that means this integration, the orientation is now counterclockwise. Sorry, counterclockwise direction. Then if you want to do it on the clockwise direction, let's say denote it with the red lines like this, you would write it as minus c f of z dz, and you can simply write it as minus of c f of z dz. That means the result is just opposite to each other, there is a minus sign in play. So how do we get this? I'll get back to it in a minute. So these are all the kind of necessary definitions that we'll need for now to deal with complex integrations that will generally involve integration along curves in the complex plane. Now, a final piece that is a definition is that the definition of the contour, because the integrals will deal most of the time will be contour integrals. So before we go to the definition of contours, I just want to state that if you have some function f of z which is continuous on C, so some prelude is that there is some f of z which is continuous on C. So what is this C? C is some curve, okay, that is parameterized by z of t and stuff like that. And if f of z of t is continuous on this interval, this is basically the same statement, but once you are just using this complex variable itself, then you are using a parameterization. It's continuous on, let's say this is the value of the parameters that takes place, that means the interval. And if this interval AB can be broken up into finite number of subintervals, in which f of z is continuous. That means you have some curve from A to B, let's say, and you can subdivide it, and in all the subdivisions f of z is still continuous. Okay, that's what it means. That's what this statement means. And then a smooth arc C is one for which z prime of t itself is continuous. So this is a continuity condition, and then we have a new definition. That means we are defining something called a smooth arc. Note that here we have used this piecewise thing. It will be important when we give the definition of contours. And smooth, what is a smooth arc? A smooth arc is just one, let's say C prime. That means, let's say you have this curve over here, and let's say this is your C prime. It's a segment, small segment. Is one C prime for which the derivative of z with respect to t is continuous. So there are two things at play. One is the continuity of f of z, and then the continuity of z itself. So keep these things in mind, and using this definition of smooth arc and the prelude that we have written over here, we can finally define contours. So the definition, contour. So what is a contour? Contour is just a piecewise smooth arc. So a contour, just a piecewise smooth arc. And on a contour, z prime is piecewise continuous while z itself is continuous. So keep this thing in mind. In general, we'll be any kind of integral that we'll be dealing in this course on a complex plane will be contour integrals. That means you can have a circle in the complex plane, a box-like region in a complex plane, or an elliptic region, or there might be regions that will look like this, or even this. There can be many kinds of contours, so we will see as we progress along. Now, since we are done defining contours and all that, let us try to see some examples. And let's say we want to integrate a very simple thing, z dz, along a circle, along a unit circle. So if this is your complex plane, then take radius 1, draw the circle. So this is a circle, right? And it exhibits the polar symmetry, so very naturally you can use the theta, the angle, to parameterize this integration. And this is a closed curve, so I should have written it like this. Alright, where C is the contour, or this circle, whatever you want to call it. So to do it, we're going to use the thing that we saw earlier, that if you have something like this, you can parameterize it and use the value of the parameters, I mean the endpoint of the intervals of that parameter. And you can use this to evaluate this integral, the contour integral, right? So we can parameterize the circle as r e to the power I theta. but r is what? R is just 1, right? So this is just e to the power I theta, and dz would be e to the power I theta I, and there would be a d theta. This is just the derivative of z. So you put all this in, and how does the parameter vary? The parameter varies from 0 to 2 pi. So this is just 0 to 2 pi e to the power I theta. Then there would be a I over here that is coming from dz, and another e to the power I theta coming from the dz. So there will be 2, that means e to the power 2 I theta, and then there would be this theta, d theta, and this is just equals to your original integral that you started with. So if you just evaluate this, keep the I with 2I theta d theta I 0 to 2 pi. So you can treat this I in the exponential as a constant. You can do that. If you do that, then you would have 1 upon, okay, what is this? This is 2i, so you would have 2i, and it will be 2i theta 2 pi to 0, like this. Okay, this 2 cancels out. 1/2 e to the power 4 pi I minus e to the power 0, which is just 1. And what is e to the power 4 pi I? Well, you can take help of the Euler's identity to figure it out. That is cosine 4 pi plus I sine 4 pi. Sine 4 pi would be 0 because sine n pi is 0, and this would be what? This would be 1, I guess. In case you get confused like me, you can always draw a graph and see how this thing goes. So this is 0 to 2 pi, right? And in the 4 pi, it would be 1 as well. So this would be 1 minus 1. There would be a 1/2. This is just 0. So this is one way to do it. And from here, you can actually see something quite interesting, is that if your function, let's say you have a function capital F of z, is analytic, and you can write capital F prime of z, which is a derivative with respect to z. Don't confuse with the derivative with respect to t. And if you can write this derivative in terms of some other function, small f of z, which is continuous in a domain t, let's say, then for a contour C lying in T, that means the contour itself is existing within that domain with the endpoints z1 and z2 respectively, then you can have this following result. So how do I get this? How did I write this whole thing? It was pretty obvious from this example, but this is just one example. Is there any way to prove it? The answer is yes. So let's start from this guy, the left hand side. So this is a proof. So this is our contour integral. We're trying to integrate this guy, but we have a very special condition that f of z, this continuous function, it is equals to some derivative of an analytic function. Okay, so let us use that. f prime of z dz, and note that this is a derivative with respect to z itself. Alright, this is still a counter integral. Now what we're going to do is that we're going to shift to the parameterization thing. Okay, and this z2, let's before we note which point is what, let's say our parameter has this interval a b, and z2 corresponds to the endpoint. That means this should correspond to the point b, z2, and z1 would correspond to point a. Okay, now let's write it like this, a to b, and we are saying that we can parameterize this, and then you would have what? Instead of dz, you would have a dz prime, but that dz prime is a derivative with respect to what? With respect to t, right? So let's write it like this. Okay, so instead of this prime, if you can write it like this, this will be more clear. And what you see on this side is nothing but the chain rule. So this is just ddt of f of z of, sorry, it should be right. This is it, and from this line you can use the fundamental theorem of calculus. So using the fundamental theorem of calculus, you can easily see that this is just f of z of t of b minus f of z of a, and finally you will have f of z2 minus f of z1, and that's it. Oh, there should be a dt like this. So this is the proof that if you have an analytic function which serves as the derivative of some other function that you are trying to integrate in some domain, the result will only depend on the endpoints. And from here, if you can see that if the contour or the curve itself is closed on itself, then the result is actually 0. So this will be an interesting thing, and we'll discuss it when we do the Cauchy's theorem. But before we finish up, let us try to see another example, that is how we can use this parameterization technique to do integration on the complex plane. So this is a very classic example. Let's say this is example number 2. So let's say we want to integrate this kind of a thing, z bar. Okay, and the contour we are considering are the first one would be, let's say this is your complex plane, and the first one is something like this. Let's call it C1 and call it C2, and this goes from the origin 0 0 to 1 0, and finally it goes up to 1 1. So this will be one part, this will be part 1, that means the C1 and C2, and then we would go another we would go from the origin to this point using another path or another line or another contour, whatever you want to call it, using, let's say, C3. This will be our part 2, and we will see that whether these two results actually vary or not. So let's get started. Z bar is nothing but x minus iy, and you can, if you have this x and y in your z's, then dz would be simply just dx plus I dy. Okay, and now you can see that I'm not using the other parameterizations because in this case it's a Cartesian form, and that's why I'm using the Cartesian form of the complex variables to make this calculation easier. If you do this using the polar thing, it would be a lot harder. So that's why you have to choose the parameterization that suits the that makes the calculation pretty easier. So instead of dz, now just write dx I dy, and you can see that there are two parts. One is C1 and another one is C2. So even though this is a general result, I'm gonna use this example to make this result understandable to you. Is that if you have some contour, let's say like this, from here to here. Sorry about that. Let's say this is one kind of a contour that we are. So this is our starting point. This is the ending point. And what you do is that you go from point A to point B, then go from B to C, then you go from C to D, D to E, E to F, and finally the ending point G. So if you call this C1, C2, C3, C4, C5, and C6, then the net result would be just the summation of all the individual contours. That means if it's Ci, let's say I is equals to starts from A and ends on G. That means you have to calculate each of these contours, and then you at the end you just add up the result. That's how it works, just like line integrals. So yeah, first you have to go from this point, let's say A to B and then C. This is the first part. You go from A to B and then from B to C. So let's not write down the limits right now. We'll do that a bit later. So this is what this is, just giving you x dx plus I x dy. Then you have minus I y dx, and finally you have plus, because minus and plus would be a minus and I square is a minus 1, so you'll have a plus y dy like this. Now you can take the real and imaginary parts. So x dx plus y dy, this is your real part and this is your imaginary part. You will have x dy minus y dx like this. Now let's consider path AB. So for AB, we can see that here only x varies, the value of y remains constant, and that constant value for y is 0. So for AB, y is equals to 0, which also remains a constant, so dy is also 0. But x varies from 0 to 1, right? So instead of doing a double integral, we have to do a single integral. That's the convenience that we get from observing this. So put y equals to 0 and dy equals to 0 in these things. So if you put dy equals to 0, this guy and this guy goes out. If you put y equals to 0, this guy also goes out. So you only have this x dx. So you have to integrate it from 0 to 1. X dx is just x squared by 2. This is just half. Similarly, for B to C, you will see that this is a vertical line. The value of x is 1 along this vertical line, and it's not changing. The value of y is changing from 0 to 1. So for BC, you have x equals to 1, dx equals to 0, y equals to changing. That means we only have to integrate over y. right? So if you do x equals to 1 and dx equals to 0, so put that in this equation, put x equals to 1 and dx equals to 0. So if you put dx equals to 0, the first term goes out and the last term goes out. So finally what you will have, putting x equals to 1 and dx equals to 0, would be y dy plus, you will have your imaginary number I, then you would put x equals to 1 over here, so this would be dy. No need to use the bracket over here, I just use it for my own convenience. And finally this guy also goes out, right? So this is what, this is just integration of dy, and you can see that I can do it like this, y plus I, or you can even distribute this integration along this whole thing. So whichever way you want to do it, you can do it, and the result is just like this, 0 to 1, sorry, 0 to 1, and this is y dy plus I dy 0 to 1, because y is varying from 0 to 1. And this is again 1/2 plus I, like this, okay? And if you just add these two results, that means call it 1 and call it 2. If you add these two, that means contributions from AB and BC, you will have 1/2 plus 1/2 plus I, which is equals to 1 plus I. This is our result for this contour. That means going from A to B and then B to C. Now let's see what happens when we directly go from A to C. That means using this contour C3. So this is the second part, C3. So let me draw it again. This is our line from 0 0 to 1 1. We just want to see that either does the result vary or not. And we were integrating this z bar dz, right? Okay. So now you can again use all these stuffs. That means if you stick with the Cartesian parameterization or Cartesian representation, you will have to come up to this point. So let's not write it again, just use the result from there. This would be just x dx plus y dy plus I x dy minus y dx, right? Let's check. Yeah. Now how does x and y vary along this straight line? Well, this is a straight line that goes along the goes through the origin, right? And any kind of straight line that goes through the origin, if you recall from real variable calculus, has this form y equals to mx, where m is the slope, and you can easily see that this guy has a slope of 1. So this is, along this line, x and y, they're equal to each other, right? So dx would also be equal to dy. So if x and y, they're equal to each other and dx is equals to dy, then we should put that in our equation over here. And let's just, you can even do it in terms of y. I'm doing it in terms of x. It really doesn't matter. So x and y are equal. So x dx, this would give me y dy would be x dx as well. So as a result, this would contribute to x dx, and this would be 0, right? Because x is equals to y. So instead of this y, put x, and instead of this dy, put dx. So they cancel each other out. So what you have is, you are integrating over x, you have a 2, you were going from 0 to 1, and you have this x dx over here, 2 times x squared by 2, that is just 1/2. That is if you do this integration, and you are getting a value of 1. As you can see that even though your starting point and ending point, they're both same in both they're both same in these two cases where you had two contours. That means two paths that goes from A to C. The results are not the same. So in general, the results that you get from doing an integration like this will be contour dependent. But we'll see that sometimes when you deal with analytic function, it's not contour dependent, and that will enable us to deform the contours. Even though, let's say, your contour looks very it's not convenient to describe this contour, and you can deform this contour into a circle like this, and you can still get the same result. So even though in general the results of integration of complex variables are contour dependent, there will be cases where it's not, and we'll see that from the next lecture. But first we'll have to discuss Cauchy's theorem as well. So this will be it for today, and we'll see you on the next lecture. Thank you.